So last time, we learned about how diffusion turns noise into data by gradually adding noise and gradually denoising. And then we learned another family of model called the score-based models, which is doing very, very similar things. And it turns out that they're pretty much the same. Especially if you scale the number of time steps to infinite, and then they both becomes this thing called a stochastic process, a continuous time stochastic process, which can be sort of formulated into stochastic differential equations. All right, so, and if you have a forward SDE, then you actually directly have a formula to tell you what your reverse process should be, which is also defined by an SDE with this score function, and then we can just do score matching to learn how to solve the reversed SDE. All right, so that was like the last question that we had in class. It's like, is there a simpler way to do this? And I think someone, after they took the quiz, they were already be like, oh, I feel like there should be an easier way. Yeah, so this is what we're gonna learn today. Okay, so let's think about this question. Let's say we're given a data point. So we only have like one image, right? What would be the simplest way to construct a trajectory from noise to this data point? Yeah. Linear combination. That's exactly correct. Okay, why don't we just do linear interpolation of the two things, right? So how exactly you can do it is basically, say like, you just like, at the beginning of time, you'll have like, so this noise is fixed, and then you have like a large portion of noise mixed with some portion of data, and then you get a very noisy data. And then as you go on, the portion of the noise become fewer, like less and less, and then the portion of data become more and more. And then you just construct a chain of very noisy to slightly less noisy to very, very clean data, right? So you could just construct this trajectory in this way. Yeah, so remember the same noise, same data. Then learning the transformation along this linear trajectory is super easy, right? Because literally what we can do is say now we want to transform from time 25% to time 50%. Then what can we do is we literally just have, you just need to add 25% more of data and then minus 25% of the noise, right? So basically, and because the delta t is the same, so we can write it in this way. Basically, just like the noisy sample at time 0.5 is equal to the noisy sample at time 0.25 plus how much time you want to progress, so like 0.25 time times data minus noise, right? So basically, generalizing it into t and delta t, this is like what you should get. And literally, when the delta t goes to 0, then you will have this velocity thing, right? Basically, this is just like tells the velocity thing. It just tells you infinitesimally. If you take infinitesimally small steps, like what is the direction that you should go? And no matter what t you're at, no matter which time step you're at, you're always going like the same speed, same direction, right? So it's just like always gonna be the difference between the data and noise, which is x1 minus x0. Okay? Any questions? Pretty straightforward, right? Okay, so this is literally what we need to learn, right? This is like literally the only thing that's stopping us from directly getting from noise to data. So basically, the simplest way is essentially to transform noise straight into data would be at training time, you first sample a noise, and then you sample a data, and then you uniformly sample a time step, and then you compute the noisy sample by doing this linear interpolation. And then you compute the velocity, which is x1 minus x0, just data minus noise. And then you learn to match this velocity. And at sampling time, after you learn this, literally you can just start from t equals 0, and then sample a noise at time 0, and then progress through the chain, right? How do you progress through the chain? You just compute the displacement for x, and then directly apply the displacement to your x to progress on the chain, and then also progress in time steps. And at the end, just output x1. Okay? Yeah, question?
You're using essentially the noise, the image noise, as sort of a generic for the image algorithm. And I'm concerned that this noise has no semantic meaning, so would it get like there's no reason why a particular Gaussian noise should map to the cat rather than the house.
Cool question. We're gonna learn that today. First of all, we're not trying to get any semantic meaning here. We're just trying to transform noise into data. But second of all, I think we're gonna like answer your question later today. Okay. Any other questions? Now you have flow matching. This is flow matching. Class is over. Hey. No, not really. Okay. Fine. But basically, the question that we're gonna ask is that, like, this is so simple, right? Like, no math, no nothing. Like, why do we need all those previous diffusion math, like stochastic differential equations? And why do we need this? Like, also, why is this even valid? Why is this the same? Why can we even do this, right? If we can just do this, why do we need to do all the math? Well, it turns out that thing also comes from math. So we're gonna learn about the math now. To understand why this is a proper probabilistic generative model, we need to go back in time into the time when people start to develop this thing. Okay, so basically back in 2018, there's this like pretty seminal paper called continuous normalizing or like neuro ODE, neuro ordinary differential equation. And then basically this guy, Ricky, who was my mentor actually, super legendary guy. But basically he was like, proposed this thing called continuous normalizing flows. And it's basically just like formulated a generative model such as it transform the samples from an initial distribution, such as like a Gaussian, to a target distribution, such as the image distribution that we want, by integrating through an ODE. And this ODE is literally just the infinitesimal change of your data should follow the velocity. And at sampling time, what you can do is you can just solve this ODE by integrating through the velocity, and then you'll be able to get a sample or like a trajectory of samples. So basically, this is like literally what we just did, right? So you have some velocity, and then you just like numerically solve the ODE at sampling time. Okay, so like how to interpret this, right? So basically just like think of it as like the wind flow transport some like water, some amount of water from the west coast to the east coast, or from like the Pacific Ocean to the east coast, let's just say. And the question here is that why this is a normalizing flow? First of all, like what is a normalizing flow? Anyone else I haven't talked to today? Nobody remember what is normalizing flow?
You can reconstruct the process.
Yes. So it's an invertible generative model, right? Yes. And the reason why this is a normalizing flow is because the streams never cross. So imagine how like you're following a stream of river or like water or like the stream of the wind, right? Like if you just follow the stream will never, like, it will always point to one direction. So it will never, like, just get if you just, like, follow the wind, you're able to basically get from one point to the other point guaranteed. So, like, deterministically. And because this process is deterministic, if you follow this wind, if you follow this flow, you're actually going to get an invertible transformation because everything is deterministic. Okay? Any question? Cool. You have a question? Okay.
Are we saying that it's actually bijection? Unless it's bijective, it can't be zero.
So basically, the way that we construct it is yeah, it is invertible. Yeah, the way that we construct it. Okay. Any more question? Cool. All right. Okay. So how does this connect to probability? Well, basically, in order for this kind of like continuous flow thing model to transport between one probability distribution to another, we need to have the following assumptions. The first thing is what we call the conservation of mass. Basically, just imagine that the wind carried a certain amount of water, and this certain amount of water never change. Like the amount of water that you're transporting never change. So no new mass is going to get added, and no mass is going to disappear, getting dropped. So like translated into probabilistic statement, it just means that the probability should always add up to 1, because otherwise it won't be a valid probability distribution. And the second thing is what we call the continuity equation, which is like not only that the mass is conserved, it's also not, you cannot teleport them, which means that everything needs to move smoothly. Everything should move like continuously. Okay, so basically it just means that the probability can only get changed continuously. You cannot just like jump from point to point because it's a river. Okay, any question? Cool. All right. So because of this, we get to define something called the probability flux. So imagine the flux is like the amount of flow, the amount of water per unit per time that's going through a certain unit space. So if you're thinking about like how the probability flows, is the probability flux is equal to the velocity times the density, sort of. So the velocity is giving you where and how fast the probability flows, and then the density is telling you how much probability there was so that it flows out, right? Okay, so this is like a visualization generated by VO. I really tried, but let's just look at it. Okay. Maybe I should put on. Okay, do that again. All right. Okay, so as you can see, as the water flows, first of all, it's in a container. It's in like a contained tank. So the probability mass never change. And second, like basically based on how fast the particle flows, like the probability density, which is like the water amount at this particular location, also changes. Okay? Any questions?
Flux in this case, like similar to like magnetic flux, they have to produce. Like it's like the amount of like.
Nope. It just, I think water is a better. I mean.
Like lines you have like.
Yeah, kind of. Yeah, it's like amount of flows that goes through a certain place within a unit amount of time.
A sphere, you take the limit and it becomes zero sphere.
Yeah, kind of. Yeah. Okay, but anyway, basically, because of this, we can actually write the probability flux in math in this way. So this is like basically like how much probability gets changed infinite through time, and then this is what we call the divergence of velocity times density. And what is divergence? Divergence is what we have seen actually last class. It's the trace of the Jacobian. What it means is basically like how much how much do you change in every direction of the flow of the data space. Okay, any questions? Everyone understand this? Yeah, this is like very physics coded. Okay, any more questions?
Direction.
Oh, D is dimension, sorry, yeah. So in every dimension, how does the thing change, basically? Oh, I think there's a P here that is getting missed. Yeah.
What's the second assumption? It says two assumptions.
Two assumptions. One is that probability add up to 1. The second one is that the thing changes continuously.
But how is the first one encoded in this?
I guess just the first one is not really encoded in this, but like you just need to have a probability that add up to 1. Yeah.
Flux is a weird word for me. Would it be weird to think of it as like viscosity, like the amount of flow per unit of time, and you're accounting for density to like?
I mean, it changes depending on the space, right? And the viscosity is like a uniform.
Sure, but like viscosity with the thing moving over time. Viscosity
is a global field.
No, flux is actually also a physics term, and it means like the amount of things that like flow out.
as physically inclined.
It's okay.
I'm just a simple engineer.
I'm also not a physics major, but you know, this is like, it's not really. I mean, it's just a term. It's not really like but like you can imagine it however way you want. But that's what it means. Basically, just the amount of things that it outflows in a unit time, basically. Yeah. Why is it noisy?
External the noisy, right?
Depending on what kind of things that you are. So basically, if you're thinking about the path that we just constructed, then yes, each xt is noisy. But this is a generalized like notion. It's like just any flow. This is the definition. Any other question? Yes.
Could you explain the terms in the divergence function again?
Yeah, I think I missed a P here actually, by the way. But basically, the divergence means that like how much probability do you change in every direction of the data space? Yeah, so that's why it's the trace of the Jacobian in every direction, every dimension here. Yeah, I missed a P here.
Sign amount add up.
Sign.
Divergence and flow matching because it's like actually tractable in this case, right?
We haven't talked about flow matching yet.
Just guessing.
All right, any more question? Cool. All right. Yeah, so this is divergence. How much probability that outflows from a given point per unit time in every direction? Okay? Cool. All right. So, like, a good thing about this thing is that we can actually transform this PDE into an ODE. All right. So what it means is that, like, so this is the correct divergence. Sorry, that one I missed a P. But basically, we can go from here, and basically you do the greatest mathematical trick of all time. You multiply two things at the same time from the left-hand side to the right-hand side, and basically this thing, because the derivative of log is equal to 1 over x, so it becomes the derivative of the log, and then basically you just apply the same thing, applying the same trick here, and then it becomes something like this. And then, like, essentially you basically just do a lot of like calculus, and then you're actually able to get an ODE of the log probability, or of the log density. Okay? And this ODE is actually equal to, so the derivative of, the total derivative of log probability is equal to the divergence of the velocity, period. Okay, any questions here? Yes.
PFS to be non-zero.
Yes. That's a great question. Yes, PFS is greater than 0 everywhere. Okay. Yeah, basically you just do a lot of calculus, and then you get this. No question? Yes.
Actually, it's true terms because it's still depending on more than a variable.
No, basically from this line, I don't know if you can see my cursor. This line is literally the formula for the total derivative, right? Yeah. No more question? Okay, cool. So basically, then you can calculate your likelihood, right? Because now you have another ODE that you can directly solve by doing numerical integration. So exactly, so how do you train your continuous normalizing flow from here? What do we think? For real? I feel like we should know. Jumping ahead. What is the, now we have a formula for the likelihood, log likelihood. You can do for the most naive thing to think, right, is the maximum log likelihood. So basically, yeah, so because you have a formula to calculate the log likelihood at any point of the trajectory, obviously you can also calculate the log likelihood of the endpoint, right? So you just do argmax of the likelihood. What could be a problem here? Yeah.
You don't have access to P0 of X0. Like
We do. We can define that. We define P0 to be a Gaussian, for example. That's fine. Yeah. Very, very good. So basically, in order to calculate the log likelihood of the data, we actually need to do numerical integration, right? But this is at training time. So that just means that we need to do many steps of integration at training time. And that thing is really, really expensive, right? Okay, what would be a better way to do this? Yeah?
If we take the gradient of the left-hand side, we get a score, and the gradient of the right-hand side removes it, right?
Even if you do that, right, the divergence is still pretty difficult to calculate. Okay, but what else? Yes.
We can use this cumulative, or we can just directly sample, so that it will be we'll end up like we'll end up with the summation.
You mean you change the integration into summation? Is that what you, yeah, but that's just numerical integration, right? So it still has a lot of steps. Can we do something that doesn't require a lot of steps? Like we just have 1-4 pass during the training time. I think someone said it before. Who said velocity before? Who did it? Oh, you did? Oh, someone? Who said velocity? Oh, okay, why? Why did you say velocity?
Because the model is learning velocity.
Okay, it actually, basically, if you think about it, right, both sampling, like, in order to sample or calculate the log likelihood, you pretty much only need to parameterize the velocity, right? So if you have a model for the velocity, then you can do both sampling and calculate the log likelihood. So why don't we just need to make sure that the velocity is correct, right? So we just need to make sure that the velocity actually match with the ground truth velocity. So you just do L2 to match with the ground truth velocity. Easy, right? What is the problem? Yeah. We're not doing maximum likelihood anymore. So basically what we're saying is that in order to do either sampling or likelihood estimation, we just need a velocity. So if we have a model for velocity, then we can do integration at inference time. We don't need to do integration at training time anymore, right? But what is the problem here? The ground truth, right? We don't have the ground truth. If we have the ground truth, we would know that a winter storm is coming, apparently. It's a Saturday, it's a very cold day, so be prepared, okay? Winter's coming. Anyway, so yeah, but we do not know. So that's why the meteorologists are changing every day. Be like, actually, I think that the storm is moving north, or maybe not. We don't know, right? So we do not know the ground truth velocity. How should we solve this? Well, basically, say we don't care about everywhere else. We just care about how the storm is going to move to Pittsburgh, let's just say. And say now you just want to, like, now you're Poseidon, okay, whatever. And then you want to transform a bunch of water or a bunch of, like, humidity to Pittsburgh so that Pittsburgh would snow. What would you do? What is the easiest way? What's the fastest way for you to do it? How would you do that? You just, yeah.
Go straight there.
Just go straight there. Yeah, that's right. You just go straight. Yeah, exactly. So basically, this is what we're going to do as well. So let's say we fix a data point. We don't care about everywhere else. We just care about one data point. And then it's usually very easy to define what we call a continuous velocity field, which, a conditional velocity field, which means that basically it just velocity is depending on the endpoint, right? And then we call the trajectory of the probability distribution that get generated along the way of that velocity field, the conditional probability path. So the conditional probability path consists of like all the PTs along the way. Okay? And here, the conditional probability path will just start from some prior, which we can choose. So it doesn't matter. We can choose the prior. And then we will always end up either directly at Pittsburgh or somewhere around Pittsburgh. So like we would just like always end up at X1 or a small Gaussian that concentrate around X1. Okay? And by the way, so this thing is called direct delta. So it just means that it's a point mass at X1. Okay, then the marginal probability path can be written in this way, right? Basically, you just like sum up all the possible like data points, and then basically just like and times the conditional probability given the data point. Then you can get a marginal. And also, just a boundary condition. Essentially, the probability at time 1 should recover the data probability. This is basically what we're trying to construct. Okay? Question? No question?
So it's just a solve.
All right, cool. So say now we have a conditional velocity here. Then we can also define a marginal velocity. What does this mean? So basically, this just means that we're sort of like apply a Bayes theorem on your conditional velocity, so that basically it's like reweighted, taking account into like basically how likely is your current noisy point, like your intermediate data point, along the conditional probability path? How likely is the data point that defined this conditional probability path? And also just like and reweighted by how likely in general of this current intermediate point. Does this make sense? All right. So basically, you can sort of like intuitively understand this as like, this is the average conditional velocity at this current location and this current time, weighted by how likely is the data point for this current location and time. Yes.
The probability, the marginal part. Then in the next slide, when we're doing it for the velocity, is it something we're doing from that step, or is it just like separate entirely?
Separate. Separate. technical difficulty. Labubu died. Oh, all good. All right. Labubu resurrected. So this is kind of like what we defined. It's not like it's two different notions. And like you can intuitively understand it as like sort of like the average conditional velocity, and then this average is like averaging by like how likely is the data point given your current position. And the data points are available. All right, does this make sense? It's okay. We'll get to it. All right. And a very interesting thing here is that the marginal velocity we just saw actually generates the marginal probability path that we want. Okay. So what it means by generate is basically just means that like the continuity equation is satisfied, the PDE is satisfied. And why does it satisfy? It's because if you just break everything down, and then you are able to get basically the divergence back. So this is just like step by step how you will get the divergence back. So you first swap in the derivative with some regularization condition. This can be done. And then basically you input your, because we know that the conditional velocity generates the conditional path, so we can input the continuity equation there, and then it becomes this whole thing with divergence. And then plug in the definition that we just saw before, we can actually get something like this. And again, pulling out the derivative here because of some regularization condition that we can satisfy. And this thing is literally just the divergence of the marginal velocity times the marginal density. So all in all, this is just to say that the marginal velocity that we defined before from the conditional velocity that we can construct can generate the marginal probability path, which is what we want. Oh, I saw so many confusion. All good. We're getting there, I promise. Okay, the other thing, which is the most important thing and the most magical part, is that actually, so this is the equation that we want, right? So this is the equation that we came up with. You just need to match the ground truth marginal velocity. But we do not have the ground truth marginal velocity, right? And it actually turns out that if you just match the conditional velocity, you're actually gonna end up with the same global optimal. You're like basically just like matching the ground truth marginal velocity is equivalent to matching the conditional velocity. Think about that. Isn't it pretty cool? Okay, why is that? Okay, so the reason why is because we can break the two L2 down into this thing, right? We saw this yesterday, not yesterday, on Tuesday already, right? And the first term for both equations are constant with respect to our learned parameter. So we're just going to cancel it out, right? And then now we get to two equations, each with two components, right? So we're going to look at the first components together first. All right, so the first component, if you look at the conditional flow matching equation here, basically this thing you can decompose it into two integrals. And then these two integrals can be like basically if you swap the dx1 term inside, so you swap the order of the integration, you're actually gonna get the first term of the first equation back. All right, this part is clear. Cool. All right. All right, now look at the second part. The second part is pretty similar. Basically, what you do is you just, starting from the second part of the first equation, and then you just plug in what we have as definition, and then you do a lot of integrals in between, and then you're actually going to wind up at the second part of the second equation. Any question? Yes? No, okay. Understand everything, everyone?
It's not even that we're sort of having a elbow type thing where we're compressing the boundary. It is
literally the same. It's literally the same. It's equivalent. It's not even elbow. No question? All right. So this just means that, like, we don't need to match to the thing that we don't know. We actually can match to something that we do know and do know how to construct, which is the conditional velocity. Okay?
Model that remembers the goal example.
Yes, pretty much, right? And then you average out, and then it's actually the same. Now let's just look at the example that we have, right? So now let's suppose our conditional probability path is to transform a Gaussian, a standard normal Gaussian, straight to a single point with constant speed. So this is a conditional, right? So that's why we can have a single point here. What do we do? Well, we first have the endpoint distribution. And because we're transforming it straight to the point with constant speed, right? So just linearly, very straight. So we can literally have a formula for each intermediate point as a linear combination of the data and the noise. And this linear combination will add up to 1, right? And the probability path can be written in this way. And most importantly, the velocity is literally just xt taking derivative of t, which is equal to theta minus noise. That's it. And this is what we're matching to at training time, which we have already seen. Yeah?
First question, so this, us parameterizing it as this linear combination, that fact is not used really in any of the other derivations, right?
No. This is what we chose. This is a design choice. So this thing is generalizable to any kind of path. Yeah.
How is the PT xt given x1 that?
How is it what?
The third line. How is the third line?
Oh, here? Well, because x0 is zero mean Gaussian. Yeah. All right. Any other? Yeah.
Slides, I don't see any like Gaussian assumption.
Oh, there's no Gaussian assumption. You don't need Gaussian assumption.
Just assume that the noise is any distribution and it still works.
Yes. Well, yeah, pretty much. Yeah. You don't really need Gaussian here.
Is there any reason other than simplicity that we're choosing Gaussian?
Here, not really. What is the other? What is the other distribution that you can think of that we can directly sample from? There you go. Uniform. Uniform. That's kind of crazy.
Previous lectures, like Gaussian assumption is used, like this closure on the Gaussian is like used in the derivation, but in flow matching, nowhere is Gaussian.
Yeah, nowhere. It's just here. It's just that, basically. Yeah.
Like we have previously seen that we can get some kind of stochastic differential equation for our scores. So here, don't we just have like a parameterization of that same equation that will get us the same result?
Great question. We're going to talk about it later. Yeah.
You're assuming that there's an assumption that I think we assumed earlier, that comes from earlier, that you said the velocity is constant. So
Yeah, velocity, yes, is constant speed. Yeah.
But is it actually constant? Because last lecture I think we talked about stuff when we actually decrease the velocity at which we're adding noise.
Here the velocity is different from previous class. So this is two different models. And the reason why this constant speed is because literally you have the t there, right? And then like literally if you derive the velocity is literally a constant, right? You have a question? Oh, okay, cool. Yes?
Can we use this to do likelihood estimation as well? Or?
Yes, we're going to talk about it later. Yeah. Anyone else? Cool. Yeah, and this is the loss function. Literally, just you learn the model should predict data minus noise. Yeah.
The velocity stays constant?
The velocity is constant only on this particular path. Only on this particular x0 to x1 path. But it's not in general. In general, it's not. Actually, I think this may answer your question. Yeah. So basically, so the left-hand side is like the path that you construct at training time. So everything is straight, right? Everything is straight. But the learned function will have this averaging effect, right? So you learn the entire field. So you don't have this straight line anymore, actually, but you have this like the slightly curved average field. Still normalizing flow, right? Yeah, because you have the one-to-one, you have the invertibility. Okay, any question? Yes.
Why is it slightly collapsing in the middle?
Because if you look at the left-hand side, right? So like you can see how the field is not like the field has a collapsing. So like the margin. So we're later on when we're sampling, we're using it as if it's the marginal, and the marginal has this like slight concentration in the middle. Yep.
So in this case, if I were to pass the same Gaussian input twice to the model, I get the same image out.
Yes, it's deterministic completely, which is different from diffusion, right? Yes. Okay, any more questions? Cool. Actually, this thing is like super cool because the same algorithm was developed by 3 different groups of people at literally the same time, like literally the same conference, and they all got into the same conference. So yeah, so the first group is a group in MetaFair, and this is the group that I interned at, actually. And then the second group, I believe, is a group from UT Austin. And then the third group is a group from NYU. And they all derive the same algorithm from different theoretical perspective and all submit to the same conference and all got in. So this is like sort of like a beautiful moment of science where you just kind of have like a collapsing ideas, but like they're from different points, you know? It's just like our, flow matching, everyone goes to the same point. Anyway. Yeah, pretty magical. But you may have this question, right? I feel like some people are having this question, but they didn't ask. So like, the marginal flow has some dips to it, right? So it's not completely straight. It's not the straightest. So is there a way that we can, like, let's say now we have trained a flow matching model now. So now we have this invertibility, this coupling already. Is there a way to make this even straighter? Is it possible?
Like new marginalized flow as you're training it and train a model to directly move from your P0 to P2.
Yeah, pretty much. So this thing is what we call reflow. So this is a technique that developed by the second group of people who proposed the same thing. So basically what you do is, now let's say you after training with the linear interpolation, you already got this coupling. So the blue coupling and the green coupling, And then what you can do is you can just like use this coupling as your new ground truth. And then instead of like randomly sampling from a Gaussian, you sample from the coupling. And then you can get the straight points. And then it becomes more straight.
Explain again.
Oh, okay. One more time. So basically, this is like your first time flow matching. So basically, after computing all the linear interpolations, you get this like slightly dipped marginals, right? You get this slightly dipped version. But now you have a coupling because the thing is deterministic, right? So you can map from one point in P0 to another point in P1. And then you just use that coupling as your new ground truth. So instead of like randomly sampling your coupling, like what we did in the original flow matching, you should use that coupling as your ground truth and train flow matching again. And then it's going to get straightened up.
Why would we want that?
Because yeah, go ahead.
Because when you sample, the more linear your flows are, the less steps you take.
Yes, exactly. So think about it, right? Like if you have, say if you have this dip, right? You have this dip, then like the safer bet for you to sample is to take 2 steps, right? Because you don't know, like basically if you only do 1 step, there can be like a lot of like discretization error that is happening because of this dip. But if you have a very straight line, then you can just do 1 step and it's straight, so 1 step is fine, right? So the straighter you are, the better you are at this like few step sampling.
How do you decide what to couple?
By your previous model, right? By the model that you learned. So this blue, this blue and green are the coupling induced by your learned flow matching model. And then you just use this coupling and then do flow matching again on the new model. Yeah.
Might be opposite, might be colliding. Is that of any?
It won't collide because it's a flow. It never crosses. Yeah. The third image is the linear interpolation of the new coupling.
Yeah, what is that showing?
Oh, this thing is just like show you the marginal, kind of. Yeah.
The green is going up, but so on the
Yeah. No, remember how this you have a concentration in the middle. You have a dip, right? So it's sort of the same thing here.
When we are doing the sampling?
No, linear interpolation is just coupling. So like you choose a sample here, you choose a sample here, and then you straight line, and then you connect them with a straight line.
Sample from both sides. We mostly connected this side to that side and that side to this side.
There's no this anymore because it won't be. Basically, the coupling tells you that you will not go to the other side anymore because otherwise it will cross, and then your stream will never cross. Yeah.
You have a data set that you know has multiple classes. Do you use this to disentangle them?
Yes, and also actually, there's another paper, I didn't put it here, that if you already have a coupling in your data set, you can just directly use it to train flow matching. You don't have to do random sampling. Yeah. I think someone has, yeah.
Your flow matching model is not perfectly trained into this process.
Then you do it, yeah. yeah. So this is just, you get it straight. It's not guaranteed that you're gonna get straight, like path on one go. It's just like, you're just gonna get straighter and straighter, kind of. Yeah, it's definitely possible. Yeah. Oh. No, okay. No, nobody? Cool, all right. So just to summarize everything, so just what's the difference between diffusion and flow matching in this context, right? So diffusion is sort of like you are wandering in the wood and with a compass, like in your hand. So you know, like you kind of know which direction you're going, but you're still like you're kind of just like exploring a little bit as well. You're just like kind of random walking a little bit. Whereas for flow matching, you don't really do random walking anymore. You just like sit on the boat and then go down the stream on the river. So this is kind of what, like to conceptually what is happening. Yeah.
Like, is this used now? Like, if it's so good, like, is this?
Great question. Do you know flux? Do you know the Blackboard that's flow matching? Yeah, this is like the state of the art, basically. It's actually crazy good. And it's so simple, right? Okay, so far we have seen so many generative models, and we know that the diffusion model and score-based model are the same thing, and today we learn flow matching. Now, the question is flow matching also the same thing? Because if you think about it, you're also like adding a lot of noise, like, and then denoise. This is kind of denoising, right? You're just like a lot of noisy samples in the middle. Are they the same thing? What do we think? Kind of, actually. So basically, what you can do, so this is what we had before, right? We have this like very straight line. But what if you define something, because the flow matching theory can be applied to any path, right? Like what Devanshu was asking. So you can also define a path from what we just learned on Tuesday, right? So you can define a V path, a V diffusion path, and you can write everything as if it is flow matching as well. And then you can actually just recover V SDE with, obviously, with the noise adding to it. And what about if we do, what about the other way around, right? Can we do score SDE transform into an ODE, a flow ODE? Can we do that? What do we think by looking at this formula? Okay. Just get rid of the G part, right? Is that what you said? All right, so basically this part looks like a velocity, right? But the problem is like the G part, the Brownian motion part, this part actually induce some probability because it's a Gaussian, right? So we still induce some probability there. So we still need to take care of that part. But it turns out that we actually do know how to take care of that part. And this thing is called Fokker-Planck PDE, all right? The name is really fancy, but basically what it means is that, like, if you have some probability in it, the Fokker-Planck PDE is going to tell you how your probability changes through this PDE that you can derive. And if you're interested in the derivation of this PDE, for the interest of time, we're not going to go over it, but it's in the Principle of Diffusion Model book, so we can take a look at it. But basically, and now we have probability flow ODE, right? So this is say we have this particular ODE, and it turns out that it's continuity equation, which is like the PD of the change of probability, which is what we learned today by using the divergence. It's actually, so if you just like plug everything in, and then you do a lot of algebra and calculus, you are actually going to get the same thing, literally the same thing. So this is just saying that the rate of change in probability from this score SDE or from this 4 SDE, they share the same, which is the same as this probability flow ODE. This and the same PDE for the rate of change for the probability means that the marginals are all the same. So this just means that now, if you have your score function, instead of sampling from an SDE, you can do ODE samples now. Yay, yay. Well, no excitement, it's okay. What else can you do with the ODE, right? I think someone said before that like we can do density estimation with this, right? So literally this is true, right? So you can literally just swap in the velocity here, and then you just like go back in time through your ODE, and then you're able to calculate the log density of your data point. Cool. And what about density estimation for diffusion, right? Oh, density estimation means that like just like to calculate the likelihood of the data. That's a great question. So for example, I don't know if you guys are familiar with RL. All right, cool. Anyway, so for density estimation for diffusion, the easiest thing is that because the loss function that we derived from 2 lectures ago is an elbow, right? So we can just directly use this elbow as an estimate of the likelihood. That's fine, but this is not accurate because it's an elbow, it's a lower bound. It's not really the real log likelihood, right? So is there another way to do it? I feel like someone here knows already. Okay, what do we think? What do we think? We know how to calculate the exact log likelihood from an ODE. What do we do? If we have a score SDE, what do we do? Use the corresponding PFODE of the SDE, right? So you just plug it in, and then it's the same thing as full matching. All right, questions? Yes.
It's like that. One more.
Okay.
Yeah. You can sample with an ODE. What is like sampling with an ODE?
Oh yes, yes. So you can sample with this ODE, meaning that like you can literally do let's see, you can literally just do numerical integration from x0, and then you do x0 plus integrate from 0 to 1 velocity, and this velocity is just this ODE.
And the sampling is only at the x0 step.
What do you mean the sampling is only at x0? Oh, you mean like to sample from a distribution? Yes, that's right. Yeah. Cool. Cool. All right. Any other questions? Oh, yeah.
A lot of PDs getting converted to ODs. Are we just doing it because it's simpler, or you want a better velocity?
No, you mean here? Here it's because it's exact. So in comparison to the elbow, right? If you compare to the elbow is a lower bound of your log likelihood, which is not exact. But here we can actually get an exact log likelihood. Yeah.
Intrinsically, it should suffer from diversity, right? Because
it suffers from discretization error. Is that what you mean? Like basically, if you take the step and then.
Because.
Well, here you're calculating the log likelihood, so it's not diversity. But yes, so like essentially, if you're sampling from an SDE, then it's gonna be because you have exploration, right? So it's more diverse than sampling from ODE, which is completely deterministic. Yeah, that's right. Any more questions? Cool. Not cool, okay.
So if I want to calculate the likelihood of x1, I first need to find the corresponding x0 for me to start integrating and.
Hey, Dimanshu, out of everyone, you should know this. But anyway, continue. Yeah.
That is important.
So essentially what you do is you remember how you reverse the chain, right? Yeah, that is right. That is right, and which is why this x0 here has a hat on it. So this is a reverse the x0. So you first reverse your sampling chain through your by backward integrating your velocity, and then during the backward integration, you can also calculate the divergence at the same time. Yeah, so you need to find the corresponding chain, which is deterministic. Cool.
Uniform is just the same.
Not really, but.
P of x0 should be constant.
Oh, you mean P of x? Yeah, P0 is constant. Yeah, that's right. Yeah. If it's a uniform. All right. More question? All good? All right. Okay, so to summarize everything, And we have seen 3 models so far. Diffusion model, score-based models, flow matching model, they are more or less all the same thing. Same, different. I feel like saying this, I'm going to offend a lot of people, but yeah, no, just like, you just add something, divide something, it's the same thing, okay. Yeah, everything's the same thing. But yeah, so yeah, congratulations. Okay, we haven't okay.
So, if we can still compute the likelihood using flow matching, why does it come under likelihood free? Like, what's the classification?
Here, likelihood free means that the training loss doesn't have likelihood. It's not maximizing the likelihood. But you can still compute likelihood, right? Same for score-based model. You can compute the likelihood through the same PFODE thing, right? Yeah. All right. So, congratulations! We've gone through the basics now. Yay! Now we know what is diffusion, what is flow matching. Yay! Yeah. So starting from next week, we're gonna be able to see like different options to further improve what we have learned. So for example, like I guess you guys have. If you guys have done the homework, you should know this by now. There's so many knobs that you can tune, right, for diffusion models, like what scheduler you use, how many number of steps, and stuff like that, right? So we're gonna learn about that. Like basically, there's a paper that like just systematically study this, and we are like. For those of you who did the homework, you should also notice that diffusion models sample really, really slowly, and it's like just like. Takes so much time. So how do we make the generation faster? And we're going to learn to do it with or without retraining of the model. And lastly, right now the thing that we learn are unconditional generations. So how can we make the generation more controllable or conditional, right? And we're actually going to learn it to do it with training and also without training, which is very interesting. All right, that's it for today. I'll see you next week. Stay warm this weekend. There's a lot of flow going on.